Okay, so, I'm always probably going to reference birds because that's my thing, but I want you to take a look that this is the same bird. Do you know what the name of this bird is? Do you know which one is the male, which one is the female? It's looking at these characteristics is very similar to functions. So this is a house finch, right? The males have the color, the red to them, where the females do not. And so when we get into, and we're still in 3.2, I'm trying to break it up and not make it as much, but we're talking about functions and we're talking about the characteristics of functions. So we talked about the different parent functions and we talked about their different domain and range. Well, on page 190, there's this new concept of what it means to be a piecewise function. Think of it, piece. So you're thinking about a piece of a function. Okay, so what this is going to illustrate by definition is a piecewise function is a function in which more than one formula is used to define on the output. Well, different textbooks use different verbiage. So I think I want to change this up here. And I want to say pretty much, somehow when I use the space, it stops the recording. So a piecewise function, for some reason I always get stuck here, so I don't know. So a piecewise function is now my tablet is not writing here. I don't know how to exit. Oh, maybe here. Oh, I see. So my apologies. So a piecewise function is a function that means defined on different domains. So you could have one function defined on one domain to get a different output. And how do we define functions? We define as formulas. And so what they're illustrating, each formula has its own domain, and the domain of the function is the union. So union means combining all of the smaller domains. That's a lot, right? And that's why we're breaking it up. So when we write our piecewise function, this is illustrating, for an example, that we could define our function to be f of x. Take any of those parent functions. So maybe we're dealing with x squared plus 1 is a quadratic function if x is greater than, I misspoke, less than 0. And then we can have the square root of x if x is greater than or equal to 0. So what this says is that this function of this quadratic is defined on this domain from x less than 0. Then you have the function f of x equals the square root of x is defined on this domain of x greater than or equal to 0. And so one of our famous functions here as piecewise is dealing with the absolute value function. So the absolute value function is that V-like shape. And on this side, x is less than 0, notice that it's a negative x, and because it has a negative slope, whereas x is greater than 0 is positive x, and therefore you have a positive slope. And what do we do with functions? Well, we're going to do a lot with functions, but there's a friendly reminder. How to? Well, given a piecewise function, we want to be able to write the formula and identify the domain for each interval. We want to identify the intervals for which the different rules apply, determine formulas that describe how to calculate an output for an input in each interval, use braces and if statements to write the function. So this is illustrating that bracey to write the function. And so let's take a look here. And this is coming from y'all's text. So what we want to be able to do, first off, is we want to be able to evaluate. If a number goes in a function, then a number is going to come out. And let's take a look here at number 46. So f of -3. Well, you have to decide where -3 lies on this interval. Is -3 less than -2? Is -3 greater than or equal to -2? Which one is it? Well, it should be the first one. So when you're evaluating f at -3, then this is going to be -3 plus 1, which is going to be -2. Then when you evaluate f at -2, well, where does -2 fall? Is -2 less than -2? No. Is -2 greater than or equal to -2? Yes. So what this is going to illustrate is -2 times the -2 minus 3. When you do the orders of operations, this product is 4. 4 minus 3, you're going to get 1. So when we conclude, this is illustrating that f, so when the input value is -3, the output value is -2. When the input value is -2, the output value is 1. Right? We're using our function notation to conclude. Then when you have x to be -1, is -1 greater than or equal to -2? Yes. And depending on how skilled we are, we could evaluate f at -1 and just do it mentally. -2 times -1 is 2. 2 minus 3 is -1. And then when you put 0, 0 is greater than or equal to -2. So f of 0 is going to be -3. And that would change, right, depending on how the piecewise function is. So then you have evaluating piecewise functions, and then find the domain for the piecewise function. And it kind of depends here, right, on how this is defined. So when you take a look on a number line for number 52, here at -2, it's not included, so you would have an open circle, but you would shade here. But here, you would have a closed circle, and you would shade here. So for number 52, the domain is -infinity to +infinity. However, what about 53? Again, you will do a number line. Here is 1. So this is illustrating at 1, you will have an open circle and shade here, but then you will have an open circle and you would shade here. So this is different because the 1 is not included. So the domain is -infinity to 1, union that with 1 to infinity, and they asked for interval notation. what would be the domain for number 54? And I'll let you give that a try. Your turn. And then you will put your results in the, we'll figure out what we're going to do with that.